So the function of integration was not invented to do backwards differentiation in a different purpose to find the areas under curves. And remember the area of a circle, pi r squared, and the volume of spheres is that. So this is talking about how basically we can utilize this formula to actually be able to find, if we look at a circle, we can utilize an understanding of a circle to actually be able to find the area, the volume of a sphere with anti-differentiation, which I haven't actually done myself. That's probably something that I'm sure Taja wanted to quickly show you, but I'm not gonna bother waste any time trying to figure that out right now. So let f(x) be a function continuous in the closed interval a is smaller than x is smaller than b, and let f(x) be a primitive of x. Then we've already been over this. So this is a repeat of the slide of the idea that we can use our basic integral idea to be able to find our definite integrals. We get our basic integral function, and then we substitute b into it, and then we subtract a substitution of a into it, and that gets us our area underneath the curve. So let's say we had a line like this, and we said the line is y is equal to 2 over 3x. If we wanted to find the area between 1 and 4 under the line, so that's this area I'm coloring in here, that means we would use a differentiation of 2 over 3x between the point 1 and 4. And we could follow this function here. It would become like this. We would have 1 over 3x squared, 4 and 1 is equal to 1 over 3 times 16 minus 1 over 3 times 1 is equal to 16 over 3 minus 1 over 3 is equal to 15 over 3 is equal to 5. So this is our general idea, and this can lead to actually quite an array of complex questions. So the reason behind the theorem. Now this is not especially easy for everyone to wrap their head around, and luckily it's not incredibly important, because in this maths course that you're doing in high school, you're not worried about writing an explanation of maths theory generally. You're going to be worried about actually applying just like the basic formulas and skills to be able to understand things. You're not a theorist, but in theory, you can imagine the blue part of this sort of area, this area here. Let me find it. You can imagine the blue area under this curve here was divided into infinitely small subintervals with a width of the difference of x. So that is our difference of x that we think about in differentiation. Now, each slice being so thin and multiplied by the height of the actual rectangle here. So this would be like all these slices sort of looking like this, infinitely thin and multiplied by the height. If you were able to get the sum of all of those together between A and B, then you would correctly get the area underneath the curve. And that's sort of what this integration is actually doing functionally. So if you want to get your head around that, and it's quite hard to wrap your head around it, it might just be good to look it up and read a little bit about it, because if, I don't know, if you're a math nerd, maybe it'll increase sort of your interest and understanding of the concepts here. Other than that, if you just want to apply it, that's what we're going to get into now. So this is an example here. We want to find the area underneath the curve. Let's say we have this curve. So this curve is just x. So y is equal to x will look just like this. Now we want to find the area underneath the curve between minus 2, let's say minus 2 is here, and minus 1. Now you might think, okay, there's a problem here. There's not actually an area underneath the curve. Well, instead we're going to get a negative area underneath the curve, because we are under the curve. So we're going to get this area in here, which is a negative area, because we are underneath the curve. So you might have a problem thinking, okay, but the area should be positive. Instead, what you consider is that you should just convert it to a net signed area. So what you're trying to find is the area between the curve and the line often. Depending on the question, what you would usually do is you would hand in a net signed area. So the area between the line and the curve is what that would be called. So this would come out as negative, as it does here. Yep, it does here. You would just say, okay, the area between the line and the curve is 3/2 units. You get the net signed area. Now this complicates things a little bit more later, or this allows some more complicated ways that we're going to deal with lines, because you might have a line that sort of looks like this. And at that point, it has these different sets of areas underneath the curve when it hits the curve, and then you have to interpret that a bit differently. So, and this is showing how you can do that. So if you have these two areas here, and you arbitrarily split them up, now you can get the area of each one separately. So that is A to C, whatever, plus C to B, and whatever's in there. And that will be the same as actually getting A all the way to B. So what you can do with these more complicated lines that dip above and below the curve is we can get A to this spot here. Let's call this C, and then C to this spot here. Let's call this D, and then D to B. And that can be our separate sets of areas that we can evaluate separately, and then we can get the sum of those areas, and that would get us the areas, the shaded region between the curve and the x-axis. Otherwise, what would happen is these areas would end up being positive, these areas would be positive, and these would be negative, and when we sum them together, when they're automatically summed together by evaluating this, the negatives and the positives would cancel out. Instead, we prefer to find each of these separately, putting absolute brackets on the outside of it, the absolute value brackets on the outside, which means even if it's a negative number, we just flip that. If it's a negative number, we flip that to positive. If it's a positive, it stays positive. So if we evaluate these separately, we can turn all the negatives into positives, and that allows us to get the actual area underneath the curve. So here's an example of them actually solving an area. So this is the equation of the curve. So if this was graphed, you would see a little x to the power of 3 minus 4x, and that's our line. Now we want to find the area between -2 and 2. And then they do it, and then you realize, oh, okay, our result is 0, which is definitely a problem. So that's why then you can separate, and that's because this area is the same as this area, except this area is negative. So then when you add them together, it's 0. If you just find one of these areas, you could double it, and that'll probably be the answer, but that's assuming that it's perfectly symmetrical, which is not really what you should do, probably. So instead, what you can do is you can get this area and add it to the opposite of the negative value of this area. So the -1 multiplied by that area. So let's actually manually do that. So we say, we first want to get -2 to 0, x3 minus 4x. So that's just this one in here. So that is equal to, we have these square brackets, we have 1 over 4 x to the power of 4 minus 1 over 2 x to the power of, oops, it's my mistake, minus 2 x to the power of 2, 0 minus 2 there. So if I substitute 0 in, that's going to be nothing, so I'm going to say 0, and then minus the second value we substitute in. So we have 1 over 4, then minus 2 to the power of 4, minus 2, then minus 2 to the power of 2. And that will give us minus 1 over 4 multiplied by 16 minus 2 multiplied by 4 is equal to 4 minus 8. We have a minus out the front there, is equal to 4. So that's our answer. So this area underneath the area underneath this side of the curve is 4. Now we could assume that this area is exactly the same, not just because we're assuming it's symmetrical, but because we already know that when we add this area and this area, it equals 0, which means this other area must be equal to minus 4. Instead of just like knowing that and putting that down in a test, a teacher might not even really realize that's how you solved it. So it's probably a little bit smarter just to actually solve it. So we're going to do another one of these square brackets over here. We're going to do 1 over 4. We're just going to copy our answers from over here. X to the power of 4 minus 2x, x squared. And this time we're going to go from 0 to 2 instead. So let's evaluate this. So our first value is 2. So we have 1 over 4, 2 to the power of 4, minus 2, 2 to the power of 2, and then minus 0. So we're just going to put 0 in those brackets because we know that everything gets multiplied by the 0. So it all equates to nothing. Now we have 1 over 4, 16 minus 8 is equal to 4. So our whole area is 4 plus 4. So a good way to sort of put these, they might have it over here. One way that you can actually one way you can actually write one of these, the formula to find the equation to find one of these relationships here, is you can say, okay, we need to split this up into multiple parts, right? So then what we're going to do, I'll give us some area by wiping everything. So then what we're going to do is we're going to it starts at minus 2. We have minus 2 to 2, and then we have our equation, x to the power of 3 minus 4x, done. And then we're adding, this is 0, we're adding 0 to 2, x to the power of 3 minus 4x. And now some of these might end up being negative, which is not what we want. So since that's the case, we just like to put absolute brackets on the outside, so absolute value brackets. So that's saying these straight lines that go down. If you did this, it's 2 straight lines around 3. That's saying that is equal to 3. So that's what absolute value brackets sort of mean in the simplest sense. So that's what we do. So sometimes a line might have, it might dip below and above the curve a lot, and if that's the case, you would have multiple sets of these absolute value brackets for different domains that exist, and each domain changes when it dips below or above the brackets. So another opportunity is another route you can go is just any time that there is a negative area, you get each area and you see it. Okay, you see, is the area negative? Okay, just make it positive. And that might be a little bit of a more consistent, easier way to go about it. Okay. So we want to find the shaded area of the shaded regions of these diagrams here. So let's do that. So I know I sort of know based on y is equal to x squared that this line hits 0, y is equal to 0, hits the x-axis at x is equal to 0. So I can just put a 0 in knowing that. So it's 0 to 3, because it gave us the 3 value there. it might sometimes give you something a bit more complicated. You know what, let's actually do a little bit more of a complicated version of this question. Let's say it asks us to find the area between the x-axis and the curve when y is equal to 0 and y is equal to, let's say, 9. Oh, that's too similar to our current question. Let's say 16. So if it told us this, find the area between the x-axis and the curve when y is equal to 16 and, for the range, I should say, for range y is equal to 16 and y is equal to 0. So that's saying, okay, we have our line here. At some point, y is equal to 16. At some point, y is equal to 0. Now, where on the line? Now, we want to find the area on the line between these 2 points. So that means when we actually differentiate, we're doing things in terms of x, because what we're looking at when we derive and when we anti-differentiate, we're looking in terms of x because basically we're working with the x value. So in specialist math, you might see some more complicated things where you actually start differentiating with y, like if x is the subject, it gets more complicated. But for now, we're just thinking, okay, we're looking in terms of x. So we can't put 0 and 16 here and then put x squared. And the reason we can't do that is because if we do that, then we're actually finding when x is 0 and x is 16. That's the actual domain for which we're looking. Instead, we want to look for the range y is equal to 0 and y is equal to 16 to find the area under the curve between the points where y is equal to 0 and y is equal to 16. So then we just have to convert. We have to say, okay, what are the x values when y is equal to 0 and y is equal to 16? So we say 0 equals x squared. That means x is equal to 0 in that scenario. So one of our values is x is equal to 0. And now one of our other values is we have 16 as, we have 16 as y, so 16 is equal to x squared. That means x is equal to plus or minus the square root of 4. The square root of 16, which is equal to plus or minus 4. So there's two values. Now, I probably should have said more explicitly, we're looking for the range, the positive range. I should have said it explicitly. We're looking for the area between the x-axis and the curve for the range y equals 0 and y equals 16 when x is above 0. My mistake. Because now there would be confusion as to whether we're looking at are we looking between 0 and minus 4, or are we looking between 0 and positive 4? But let's just look for 0 and positive 4. So we're going to say equals plus or minus 4, and we're going to look at the positive 4 value. So now we have what we're looking for this different question I've defined here. We have 0 to 4. That's our domain, because that domain defines the same range. When x is equal to 4, y is equal to 16. When x is equal to 0, y is equal to 0. So now we have x squared in this integral. So that would become 1 over 3 x cubed. And then we have this range here. So that would be 1 over 3, 4 cubed, subtract 0 in brackets there. So then the area beneath the curve is, they handpicked some things for it to be 3, so it's a little easier to work with. But we can find the area still. So we have 1 over 3 times 64. 1 over 3 times 64 minus 0 is equal to 64 over 3. So that's our area beneath the curve between the points where y is equal to 0 and y is equal to 16 on the positive side of the x-axis. So that's sort of a slightly more complicated question you'll get. There's just the extra step of finding what is the x value there, because they might give you a y value. They might give you some other more complicated things as well. Like they might say, oh, there's 2 points where the 2 points where the line, what is the area on this line under this curve between the 2 points where it hits the x-axis. So if you had a line like this, let's say this is a parabola, it could tell you just find the area beneath there and the parabola is equal to this. And then you would have to manually find what are these points here. So that's just another level instead of it giving you these points. So let's do this question here. Find the area, find the shaded area underneath this line between 0 and 16, and the line is y is equal to the square root of x. So let's attempt to do this. So we have 0 and 16. Those are our x coordinates that we're looking between. Then we have the square root of x. This is the same as x to the power of 1 over 2. X to the power of 1 over 2. So if we're applying our formula, we would see, okay, that is equal to 1. And when you have 1 over 2 and stuff, it can be more easy to apply the formula that we have all the way like at the very, very, very start. This formula here, if you know this formula, it can be a bit easier to apply it. It can make things a bit easier when you can apply it to like you have a square root that you're looking at. So we have 1 over 2 plus 1 x 1 over 2 plus 1 there. And that's what we're worrying about here. So that's 1, and then there's 3 over 2 down here, plus x, 3 over 2. Getting there, 2 over 3, 3 over x. Okay. Okay. So now we can substitute our values in, as we usually do. We have 2 over 3 multiplied by 16 to the power of 3 over 2. Subtract, and then we can just say 0, because we know that 0 gets substituted into the only term, so the term is 0. Now, this doesn't look very fun to actually solve by hand, so I'm just going to plug it into a calculator. It'll make my job a bit easier, because a lot of these questions you will actually have calculator. Okay, so this comes up with 42.6667. So you're probably supposed to do this by hand because it doesn't look like a very pretty number on the calculator. Well, I guess what looks like a pretty number on the calculator is one that looks like you really can't do it by hand. But for now, we'll just leave it like this instead of bothering to do it by hand to expand any of that. It could even just be you leave it in this form as well. Instead of bothering to do it for a lot of questions, you can get full marks for leaving it in that form. So now we're going to look at the area between two curves. So this can get pretty complicated, but at a basic level, what we're worried about is, okay, we want the area between this curve and this curve, which is just a straight line, it's not a curve. What we can do is we can get the area under this one here, and then we can get the area under all of this one here. So let's say we get the area under the linear line, and then we get the area under, let's say this is some sort of logarithmic line, so a sort of exponential line. Then we can subtract the area underneath the linear line with the exponential line. So again, let's say it's even simpler if we have two linear lines. Let's say we want to get this area in here, and this line is B and this line is A. we can get the area of B minus the area of A, and that will give us the area under B that isn't under A, which is the area between B and A. So that's the basic idea. It can get a lot more complicated because it could be like, for example, you have this line here, and you want to get the area like between here and then between there as well, and then down there as well. And that could be a shaded region on the graph, and that would be really complicated to solve all of that, because these are actually 3 distinct areas you would have to get. 4 distinct areas you'd have to get, because you'd have to get, well, you'd have to get one area here, one area here, one area here. So there's a bunch of areas you'd have to find to be able to solve that. That is like a complex question that you could get on an exam to look at a sort of set of lines and find certain shaded regions between them. This is a pretty simple version of that. We just have 2 lines, there's one shaded region between them. So then we just have to find sort of where they collide. So that's our x values that we're going to look between, where they hit each other. And then when we do that, we're going to be able to get the area under the top curve minus the area under the bottom curve, and that's our answer. So let's say we wanted to do it here. We could try to do it we could try to do it here. So first we need to find we're going to assume that they collide at 1. We're going to assume that they intercept at 0, sorry, not 1. But they also intercept at 1. So we're just going to use the area between 0 and 1 here. And x squared seems to be the line on top. So we're going to do x squared to get this top area. So when we get x squared, we're going to get basically this whole area in here, right? But then if we can get the area down in here, we can subtract that from our x squared. So it looks something like this. That'll be our answer. This, if we can evaluate what this is equal to, we get our answer. So that's 1 over 3 x to the power of 3, 1, 0, subtracted by 1 over 4 x to the power of 4, 1 over 0. So not 1 over 0, 1, 0. Now we're going to evaluate each of these separately. So I'm going to put big brackets for the first one and then negative big brackets for the second one. You know what, we're going to need more space than this. Put it over here. Big brackets for the first one. Subtract big brackets for the second one because there is that negative value there. So we're going to substitute in 1. That's 1 over 3 times 1 to the power of 3. Then we don't need to bother about the 0 because the 0 will, you know, just cancel everything out. Subtract 1 over 4 times 1 to the power of 4 minus 0 there. So that's equal to 1 over 3 minus 1 over 4. And that's everything. So that's our answer. That's our area underneath that curve there. Which would be 3 over 12 minus 4 over 12. Other way around. 4 over 12 minus 3 over 12 is equal to 1 over 12. So that's our idea. Basically, we find the area underneath the top one, which would be all this area, and then we find the area underneath the bottom one, which would be a little less area, and then we subtract the bottom area with the area of underneath the top one, and that gets us our overall area. So we can apply that a little bit more here. Now this one's a little bit more complicated because we only want to integrate this one in here between these two areas, whereas we want to integrate this one out here between all of this area. So let's do each of those steps quite separately. We go from -2 to 2. And we're going to put in 4 minus x squared. Now that will result in 4x minus 1 over 3, x to the power of 3. And then we have a 2 and a minus 2 that we have to substitute in. So that's equal to 4 times 2 minus 1 over 3 times 2 to the power of 3. Subtract 4 times minus 2 minus 1 over 3 times minus 2 to the power of 3. Equals 8 minus 1 over 3 times 8 minus negative 8 minus 1 over 3 times negative 8 equals 8 minus 8 over 3 plus 8. And that is, so this would become plus, so minus 8 over 3. So our first area is 16, and then we subtract 16 over 3. And we'll just leave it like that for now, as we get our second area. So now we want to get the area in here. This area is probably a lot smaller. So we'll do that all the way over here, where I'm starting now. 1, minus 1, and then 1, and then our line is 1, and then subtract x squared. So this becomes something like x minus 1 on 3 x cubed, 1 minus 1 there. So that's going to be our area. We have 1 minus 1 on 3 minus 1 minus 1 on 3 times minus 1. So that's 2 minus 2 on 3. So that's our second area. 2 minus 2 on 3 is our area in here, whereas 16 minus 16 on 3 is all of our area here. So we want to get this and subtract that. So we'll do that over here. Everything's a bit all over the place because we don't have too much space. Subtract 2 minus 2 on 3. So it becomes 18, or 14 minus 14 on 3, which becomes 30 plus 12 over 3 minus 14 on 3, which is 28 on 3, I believe. Yep. So that's our area. We have 28 on 3, and it's good to do units, so you can just write units squared. That's something that I forget sometimes. It's good to put units in there because we are getting like a squared area. So it's definitely good to put units. Sometimes you'll get a problem-solving question which will actually rely on you putting, meters squared in there or something like that. Next we have this area here. It tells us the area between these two lines, which does make it easier. Again, often you would have to, do something like, let's say, simultaneous equations to actually try to find the point where these two lines intersect. That would be like a complicated scenario. So we want to find the area underneath all of this, and then the area underneath just this one, and subtract the latter from the former. So let's utilize this space in here again. The antidifferentiation of, something that would be good to do here actually is to get everything in terms of, to get y to be the subject of everything, because since we're doing the differentiation in terms of x, that's what we need to do. If we were to try to differentiate y, we would have a problem because we would actually be finding the area here. like a horizontal area, which is sort of interesting, and you might deal with that in specialist math if any of you are a specialist math student. So let's first try to evaluate how do we get this in terms of x. So y is equal to the plus or minus the square root of x. Now, this isn't necessarily a function, which could make our job a little bit harder, but it doesn't, because in this range, we should be able to just consider one form of x. So here we know that x is always positive. We're always looking at we're always looking at a positive y value and a positive x value in this range. So we're just going to consider y is equal to the square root of x, so plus instead of negative. Because what this line will look like is it'll be symmetrical and it'll go down here as well. So if we were to look at plus and if we were to look at minus x, we would be getting this area in here. That's what we would be looking for if we wanted to look at minus x. We don't want to get that area. We want to look at the positive area that x is in up here. So we're just going to interpret plus or minus x, the square root of x, as just the square root of x. Now we have x is equal to 3y minus 2. That becomes 3y equals x plus 2, which is y equals x plus 2 all on 3. So let's get this top area first. We have the integral of this range here. We have 0, we're doing 1 to 4 this time actually. 1 to 4 square root of x. That's equal to, now we might have back here, do we have an example of us? I think we've already done integrating the square root of x, but we'll do it again. It should become 1 over 2 plus 1 x 1 over 2 plus 1 there, and that's what it looks like. And then we need to make sure we remember to put our boundaries in there. So we just apply, our typical method of finding the area by expanding these square brackets. Okay. So I'm not going to simplify this yet because this other line that we're looking at could maybe simplify it. Probably not though. It looks like a pretty simple linear equation, which means it probably won't simplify it any further. But I might just plug it all into the calculator at the end lazily as well, which I think can be productive, considering we only have about like 5 minutes left or something. So let's look at finding the differential of the bottom line so that we can subtract it from this value here. So it's a linear line. That makes our job pretty easy. We go 1 to 4, and we have x on 3 plus 2 on 3. So that becomes, well, that equals is a better way to put it. One on 6 x to the power of 2 plus 2 over 3 x. And we need to remember to put our 4 and our 1 here. Now we can open this up into being 1 over 6 times 4 squared plus 2 over 3 times 4 minus 1 over 6 minus 2 over 3. And that's our expanded form. Now we can throw everything together. So it becomes 2 over 3. So we're getting this this top line area, 2 over 3 times 4 to the power of 3 over 2 minus 2 over 3. Then we're subtracting all of this other line that we've found, all of this other area. 1 over 6 times 16 plus 2 over 3 times 4 minus 1 over 6 minus 2 over 3. So some things cancel there. That's 2 over 3 times 4, 3 over 2. This cancels that one there. Minus 16 over 6 plus 8 over 3 minus 1 over 6. And we could keep working to simplify it, but I think, how many slides do we have left? We have a fair amount of actual content to get through, and I think everyone knows how to sort of go down and spend a lot of time simplifying all of those processes. So last, we're going to look at the trapezoidal rule. So basically what this is sometimes we might need to actually estimate what is the area underneath the curve instead of being able to actually find it. There's certain reasons for this. Sometimes we aren't able to find the antiderivative, so we will want to estimate what's underneath the curve. So the true area underneath the curve would, include all of this area underneath the blue stuff, but we can sort of estimate it with these trapezoids we've created in this diagram. So these trapezoids cover this area here. They don't cover all the blue area, or sometimes they go over the blue area. But that's the area we can use to estimate what is the area underneath the curve. So we've separated a line into segments, which we place trapezoids over, and then we get the area of the trapezoids, and that's how we find the area. So the area of one trapezium, that's probably in your formula sheet, will be h over 2, that's height. So in this scenario, we're actually considering height along this way. That's sort of the height of it. And a plus b, a is this, how high it is this way. So don't consider this height for now. Just consider this. Consider h width in the example of the trapezoidal rule. We have height goes along this way, and a is how high it is this way, and b is how high it is that way. So the area of one trapezium is sort of like this. A, A1, and H. Perhaps it would be better to do A, A1, and H. Then we have our second trapezium, which is connected. So, if we have our trapezoidal rule representing a line, there'll be a set of sequential trapeziums that might represent, a curve. So then A1, and then there'll be A prime, and then A double prime, then A triple prime. Those represent subsequent heights of the following lines. So our first trapezium has A and then A1 as its heights. Our second trapezium is A1 and A2 as its heights, because it shares one wall with our first trapezium. So there's A1 there, there's A1 there. Then our third trapezium would have A2 as its first wall, and then A3 as its next wall. And then you can continue that until AN plus B, plus the final height that we're worried about here. So that's basically what we're doing. We cut this line into evenly spaced segments, and they have to be evenly spaced because our spacing is H. And then we find the area of different trapezoids that we're able to cut out of our line. Now, if we sum all of that together, you'll find that you can put it in this form here. You can put it in the form of h over 2 outside of everything. You can go a plus b, so that's the height of the first wall plus the height of the last wall. plus 2, A1 plus A2, etc. So those are all of the inner walls. And that's because there's 2 instances of A1, there's 2 instances of A2, and there's 2 instances of every one of the inner wall. There's only 1 instance of each of the outer walls, and everything ends up being multiplied by h over 2. So that's what the trapezoidal rule becomes. I think it's in your formula sheet. If you're able to plug things into it properly, you'll succeed. You'll be able to estimate the area underneath the curve using that. So our last bit of work probably will have to be us. I'll quickly look at what we have ahead. Our last example will be us looking at actually applying this trapezoidal rule for this function here. So we want to estimate the area here. So we're not actually going to do the integral, sorry. We're going to find the area at different points. So with 5 function values, estimate. So that's saying with 5 different points along the line. We're going to just do 3. We're going to find 3 points along the line. So we're going to do 4 is probably the easiest actually. So 4 points along this line. Let's find the value here. We have 0, 1, 2, 3, 4. We'll keep 0, so it will actually be 5 values. That's my mistake. Now, we want to, so the line, let's say the line, it could look like anything. Let's say it looks like this. We want to chop it up into distinct parts, 5 distinct parts at 0, 1, 2, 3, 4. That means h is equal to 1 because the width of each one of these parts is 1. Now that means we actually have to find the height of each of these parts as well. So we have to find the height at 0, we'll call that A, then we have A1, then A2. So let's do that. So at 0, the height is 0 because we can see there's a leading x, which means if y is equal to x4 minus x and x is equal to 0, then y is equal to 0. When x is equal to 1, we want to find what y is equal to. So that's y is equal to 1 and then 4 minus 1. So that's y is equal to 3. Then when x is equal to 2, y is equal to 2, 4 minus 2. So that means y is equal to 4. When x is equal to 3, y is equal to 3, then 4 minus 3. So y is equal to 3. Lastly, when x is equal to 4, y is equal to 4, and then 4 minus 4. So y is equal in that scenario to 0. So what we have is we have this sort of symmetrical looking line, and we have 4 different heights that we have. We could try to sort of plot the heights of this line. So let's say we were looking here. At 0, we know the height is 0. At x equals 1, the height is 3. At x equals 2, the height is a bit higher at 4. Then the height goes back down, and then it goes back down to 0. And those are our parts that we're going to separate into different trapeziums. So now to do that, let's actually just throw everything into this formula. So we have all these 4 different heights. We can put them next to each other like this: 3, 4, 3. So that's x, that's y, 3, 4, 0. So our trapezium rule would say we have h over 2. H is 1, so it's 1 over 2 multiplied by 0 plus 0. So that's our A and that's our B, our first value and our last value, plus 2 times everything else. So that's 3 plus 4 plus 3. So that's 1 over 2 multiplied by 2 this time. So it just becomes 3 plus 4 plus 3. So our estimated area, not the true area, our estimated area is equal to 10. And that's our result. So basically, in simple, what we're doing is we're basically using a simple mathematical formula that I believe is on your formula sheet to estimate the area by separating a line into approximate trapeziums that cut up the line into these approximate parts.